some intricacies of the 1D property for beams. Just about every problem that I've done with beam, if we dealt with a particular sketch or a wireframe, then the beam cross section was constant. So suppose we have a tapered beam like this, where the left side is has a certain circular, has some radius, and the right side is 3 times that. The left end of the beam is clamped and is subject to an axial load of 1,000 pounds. Okay, so let's go ahead and make this. We're going to start with a part file. We're going to make a line that's 10 inches long. So, for example, on that plane, I will make a line 10 inches long. Okay, let's make this in 10 inches. All right, and exit. Now remember, because I'm doing this thing in a sketch as opposed to a wireframe, a line like that, I need to join this, otherwise I won't be able to mesh it with beam elements. Okay, and we're going to apply material property on it. It really doesn't matter, it's irrelevant for this problem. I'm going to make it out of aluminum. Okay, and then we're done. So we're going to go to generative structure analysis. Oops. Generative structure analysis. Because this is not a solid object, we're going to have to measure it ourselves right there. See that beam measure? I'm going to click on that. And actually, let me make these. Sorry, let's go back here and make each one 1 inch long. So there's going to be 10 elements there. Okay. If you want to look at it, right. So this is 10 inches long. This is node, where's node 1? It's probably on this side. This is element, okay, let's see now which one is this. This is element 1, nodes 1 and 2, etc. So there is actually 10 elements there. So let's deactivate this. Cross-sectional property. Well, first of all, let's say the left side is clamped, this end is clamped, okay, and we're going to apply a force on this right side. The force of 100 pound right there, and in the negative x direction, negative 100. You take this thing out. Okay, so this is under tension, as you can see. All right, what about the cross-sectional property? So what we're going to do is this. Our beam is tapered, as you can see. However, what I'm going to do is I'm going to assume that I'm going to give it a value of 0.01, and then you see how to make sure that it goes from 0.01 to 0.03. Okay, so let's go here. 1D property, which is right there, and it is circular, cylindrical beam, and the radius is 0.01 inch. Okay, and we select the support. There's a support, and let me just check something, whether I wanted 0.01 or 0.1, because I'm going to compare it with some analytical calculation. I want to see what I have for my radius in the, yeah, 0.01 is good. Okay, good. Yes. All right, so back there. Now, we have, this is going to be, there's no offset. There's no offset. The concept of offset was discussed in the previous video segment. There's no orientation point because it is actually cylindrical. Orientation is irrelevant. But notice that here, there is this thing called variable beam factor. So if you check it, then you get two numbers, starting factor, ending factor. So in my case, starting factor is 1, okay, and the ending factor is 3. Now, I may have to come back actually, and change these, flip these around, because I'm not sure where my start or where my end is. So we say OK. Now let us run it. So remember, this is not actually showing you this is, if you zoom in, you can probably see that. Let me show you something here. Let's go back to properties. Ordinarily, it should show you what the section looks like, but this is so small that you can't see it. Let me just temporarily change this thing to 0.1. There, you see that? It's right there, 0.1. However, because it's 0.01, I can't even see that. Okay, so it was correct. It's just that you have to zoom in so much that it's not worth it. All right, let's run it. Not a big deal. This is basically a bar under tension. And let's look at the, first of all, deformation or displacement. Yep, you can see that. All right. Now, Catia cannot plot. The only plot that Catia can provide you for beams is principal stress, the axial stress. Okay, so let's go and plot the principal stress right there. All right, so look at what happens. This is the clamped end. The clamped end is right here. Okay, and its area, its stress actually, it's small, much smaller compared to the other side. What this means is that actually that factor should be flipped. Okay, so because the intention was for this end to have a small cross section, large stress, and for that end to have a big cross section and therefore small stress. So this factor, I need to flip it. 3. This has to do with how the line is drawn, and you may want to fool around with it and figure it out. But let me run it now, and now the biggest stress is going to be at the clamp because the area is the smallest. So let's plot this. Right there. Okay, so how good are these? Well, let's see now. This is the axial stress in the first element, the element where the cross-sectional area is the smallest. Okay, 2.63 10 to the 5. Now, if I wrote a simple MathCAD MathCAD program, here is the radius. Left side is 0.01, right side is 0.03. Okay. And this is the way the radius is along the way. It's linear variation, and the area is given by that, pi r squared. Force is given, and the stress is force over area. So if you look at the value of this stress at different locations, for example, at 1, theory says it's 2.21, sigma at 2 is 1.64, and at the very right hand side, sigma at 10 is 3.537. This is the variation of stress from the clamp end, which is the left side, all the way to the loaded end. So, for example, if you look at this, this was pretty reasonable, 2.26 or 2.63. It agrees with these values. Okay, and if you go at the very right hand side, the smallest stress is where the load is applied, is right there, 3.78 10 to the 4 or 4 10 to the 4. So it agrees with here 3.53. Okay. So anyway, I just showed you that it is possible to create tapered bars in Catia. My video card is not working with this average ISO. So let me put it back to symbols. Okay, right there. Okay. So that was the purpose of this presentation, to show you what is the role of this variable beam factor. Okay. So there will be a third video segment that I'm going to prepare about beams, again, intricate aspects of the beam, and we're good.